More candies. Candyman. Hmm. Okay, so who wants to change your major to dentistry? Well, you cannot because you cannot operate on yourself, so it won't help you. It's possible. It is possible using robotics. Yeah, and I'm pretty sure it will come one day within your lifetime. Yeah, well, yeah, it's already useful for a lot of things. All right, so back to today's lecture. Okay, it's all going to be coding and stuff that I want to illustrate. So let me see which shell is good to use. This one is good. All right, so we're going to take a look at string length. Okay, so quit this and we'll take a look at, I'll just call it length. Okay, so view int, um, we'll just use the usual one. Well, maybe we should use the one that I intend to convert into TTP ASM code. So this is only going to be a very limiting, string length function. You have to give it a const char star. This is the actual pointer to the string, and it has to return the length of the string. Okay, so what is const doing here? What does it do in the C program? Yep. hmm And why is that helpful? Because I'm not going to change it anyway, so why do we need a const keyword here? Yep, because it's a rule in case I specify any code to change anything that string points to, the compiler can now come back and complain to me and say, but you said you're not going to change it. Yep. It does not automatically improve performance. It does when you use it kind of very systematic way, and the compiler also makes use of it. But any const pointer can be changed to non-const. Let me illustrate. You can say char bob this, and then the reference the uh, casted one, and then we'll just see whether this compiles or not. All right, so we'll just say, okay, is that going to compile? GCC compiles just fine. Okay, then you guys would say, but Tack, you forgot to say warn all. Yep, so if you say warn all, it controls, this is about main not returning a value. It is not the problem that we have, okay? It's complaining about this. So let's see again. Okay, does it, line 5. Okay, maybe it is about that one. Oh, it's about not returning anything. Fine, okay. There we go. Okay, so you can cast a const pointer back to a non-const and then mess around any way you want. Because that's the whole idea of C and C++. It trusts that you know what you're doing when you use casting. They go like, okay, if you say so, fine. Yep, yep. And in a lot of contexts, it doesn't even give you, it doesn't need you to do the casting either. Pointer stuff, yes, you do need the casting, but if you go from like a big integer to a smaller integer, that promotion and demotion is automatic, which is sometimes not nice to have. Okay, all right, so we're going to focus on string length. We'll first start with the most boring way to do this. Okay, this is absolutely the most boring way to do it. So we start with the actual length and we'll call it count. Count starts with a 0. And then we say, we make another pointer. Okay, we say you char, it has to be const again. We call this PTR. Okay, So we'll say PTR is initialized to be the same as STR, and then we say as long as whatever PTR is pointing to is not the null character. Okay. What we'll do is to increment count. Okay, like so, and then when this is all done, we return count. Okay. So now we test this code. This is result, and then we say result equals to length of tag exclamation point. Okay, there we go. Okay, so we probably can expect this to return a 4, into result by the time we get to line 17, right? Okay, so are we all kind of understanding the C implementation of length at this point? Yes, go ahead. Hmm? Yes, it does use 5 bytes, but string length does not include the null character. Yep. So, yep, it doesn't matter because I'm not using the result of this expression. So pre-increment versus post-increment versus, the long way of saying this versus the not so long way of saying this, but still doing the same thing. They are all equivalent in this case. So it's just which way do you want? Okay. So I personally just do a pre-increment, post-increment, doesn't really matter. Yep. Okay. All right. So we're gonna compile this code and run it and see if it works. So GCC again. Yeah. Okay. So it's okay. This is just why is it not used? Oh, okay, because I put a value into result and then I don't use it anymore. There's no read access to the variable. I just overrode it, and warn all just says, okay, so why do you even put it into this variable to begin with? Okay, but it's not an error. It's just like, okay, this seems pointless to the compiler. That's okay. We'll just tell the compiler to do it, which it did already. So now we look at this program, we get to, oh, this is the wrong program. GDB length, there we go. Put a breakpoint on line 17, run it. Oh, I forgot to increment the pointer somewhere. Yep, okay, very good. Which is my favorite mistake, forgetting to increment things. So in here, we can increment PTR. Okay, there we go. Compile the whole thing again. And then GDB the whole thing again. Put a breakpoint on line 18, run it. What is the result? 4. Okay, not terribly exciting, right? Okay, this is the super lengthy and boring way to do it. Okay, so what we'll do is we're going to keep different versions of the same code, okay? Because then we can diff, okay? So we'll copy this, okay? This is what I taught my previous class. If you don't know how to use GitHub, at least do something like this, okay? Length 2025 1110 underscore 1038, okay? I always include the time too because I make multiple changes within the day and I want to remember which one is the one that I did at what time. Okay, so this is always the way that I quote unquote save a copy if I don't use get. Using get obviously is the best way to do it. Okay, so we can now diff the program once we make some changes. Okay, so we look at this program again. Oops, link not yes. There we go. Okay, so the first change I'm going to do is like, if I am incrementing PTR and I'm incrementing count at the same time, that sounds like duplication to me, and it is duplication. As it turns out, I don't need no stinking count variable here if I already have PTR, because what I can do is to say, let's just subtract the pointers, okay? We'll subtract, str, we'll subtract PTR from str, the difference between the two pointers will tell me the number of chars in between. Okay? So you look at this and go like, really? Is it going to do that? Yeah, it's going to do that. So we'll, No, I'm actually subtracting 2 pointers. The 2 pointers are pointing to different places, and I'm looking at the difference divided by the the size of each thing that it points to. Now, each thing that it points to is a char, only takes 1 byte. So that's why it's only dividing it by one, which means it's not doing any actual division. But if the pointer is pointing to something that's more than a byte, it would actually divide it by the size of the thing that the pointer points to. So um, I mean, it's not super important in this particular discussion, but I think it is nice to know, you know, the actual distinction. So, oh, okay, it got it wrong. Yes, okay, finally the program got it wrong. So we'll go ahead and say, I think I know what is wrong with it. I think I did the subtraction backwards because 252 is -4. Do you guys recognize that? Because 255 is the same as -1 when you look at an 8-bit representation as a signed number. So 255 is -1, 254 would be -2, 253 would be -3, and then 252 would be -4. So what are the chances that I'm getting the arithmetic negation of what I'm supposed to be getting? So I think that's reasonable to say maybe I switch the side of the subtraction. Okay, so let's go ahead and check that out. Okay, because str is where it starts, ptr is where it ends, so it really should be like that. There we go. Check again. db list. Put a breakpoint at line 15. Run. Print result. Oops. There we go. 4. Okay, we're good. All right, so let's go back to the program and see if we can make it even better. Okay, without going for the recursive route yet. I don't think I can do it without a local variable, so I still need a local variable. And I think this is the best way I can do it, is to use a pointer instead of a counter. Okay, so we'll just say, okay, this is the best we can do. Are we good so far? This is the best non-recursive way of doing it. So when I say something like that, what does it imply? There's a recursive way to do it. Okay, so we'll do it in a recursive way, but before we will copy this program again to a backup. Okay, so 2025 1110, and the current time is 10:42. Now, obviously, this approach does not help if I can make more than one changes per minute. But I typically cannot, really work on my programs, multiple times per minute. So I think realistically speaking, it is okay. Hmm? Then what if I make changes in the next minute? It doesn't scale. Yep. All right. So we're gonna look at this, and now we look into a recursive way of doing this. I like recursion because recursion usually means you don't need as many local variables. You don't need to track the state as much. So I'm going to use the non ternary expression first. So everything is in a conditional statement. Okay, that makes it a little bit easier to read. So I would say this, if this is not, okay, the null character, we do one thing, otherwise we do something else. So if it is not a null character, it is the recursive case. If it is the null character, it is the non-recursive case. That means for this particular string, the length is 0. Does that make sense? Okay. The pointer that's supposed to be pointing at the first character of a C string is already a null character. That means the length of that string is 0. Okay. So what about the recursive case? Then you go like, well, I witness one non-null character, so I know there's at least one. What about the rest of the string? Let somebody else figure that out. All right. So we're gonna do it this way and see if it works. Okay. This is supposed to be the same as the iterative approach. Okay. So we'll save this, GCC it, GDB it, put a breakpoint on line 14, run it, and then we print, what was it? Result 4. Okay, cool. So now we'll refine this a little bit, okay, just a tiny wee bit. And then we go back here and we go like, look at this. It has both return statements are in the middle of a conditional statement. I mean, you can do it, but to me, it's kind of like a taboo thing. Okay, I don't like to put return statements other than at the very end of a function. So if you ask different people, different professors, they have different views on whether this is acceptable or not. Okay, most people say this is acceptable. I just don't like the idea of allowing returns in the middle of anything because that really messed up code analysis. Okay, now for something as simple as this, it's not a problem. But where do you draw the line? Okay, it's a slippery slope, better not to get onto to get on in the first place. Okay, so to me it's like, okay, that's not what I like. So instead of doing this, we'll just have one single return statement and turn the conditional statement into a ternary expression. Because look, if you look at this one here, it is a prime candidate to turn into a ternary expression. Okay, so in the process of turning this into a ternary expression, I will also start to use slightly more cryptic ways of expressing things. So we'll just go like this one is 1 plus the length of string plus 1, otherwise return a 0. And now everything is on a single line. Okay, but let's double check to see whether this code preserves the same meaning as the previous one. So now we GCC, GDB, list the program, put a breakpoint on line 10, and then we run the code, print, result. Aha, still works. Cool. All right, so I think we are ready to kind of move on to the assembly language implementation. Yes, expression. I have a really snarky answer. I'm not really sure I want to share. I'll share anyway. I know I'm getting recorded too because I'm the one recording it. So bite me. I think people who think that way, why did they get into programming to begin with? That's kind of my way of looking at it. Because ternary expression is really powerful as a technique. Because if you think about conditional statements, it is expressing branching at a statement level. So that means if you have two function calls that look otherwise almost exactly the same, but depending on a certain condition, you have to modify one of the arguments just a little bit. Using conditional statement, you would end up with two different function calls that are highly almost exactly the same with the difference of one single argument. And every time you look at your code, you identify, okay, earlier I was in the CISP 300 class, and I was already talking about abstraction, pattern recognition, and why it is important in software development. Because every time you see something and go like, hey, these two things look almost exactly the same, then you really should ask the question of, can I combine those two into one single thing where the only difference is reflected as locally as possible? And that is why I personally think it is good to use ternary expression. And the more you use it, the more you're used to it. And so people who say that this is too complicated and difficult to read has to do with they don't use it enough. That's my view. I mean, those other people can disagree with me and bite me. Or as Bart Simpson says, eat my shorts. Yep. Hmm. To quote Sifu from Kung Fu Panda, there is now a level zero. That is correct. So recursion is less efficient because there's a whole bunch of stack operations that you don't need otherwise. But recursive functions are also easier to prove that they are correct because in mathematical proofs, there's a technique called proof by induction. So when you look at the structure of a proof by induction, proof as in proof by induction, it resembles recursion code. So recursive code is very easy to prove mathematically using the technique called proof by induction. So it's a different way of looking at things. Everything that is recursive can be turned into non-recursive. Everything that is iterative can also be turned into recursive. So those two have exactly the same expressive power as to what it can express in terms of algorithms. In terms of efficiency, as we already said, iterative approach is a better one because it's more efficient. But but in terms of simplicity, look at this code here. It is actually more, it captures the logic in a simpler way. Okay, that would be my way of saying it. It'll be more efficient. Yep. hmm So we're gonna go with this approach in the assembly version. Okay. So we'll go ahead and just kind of do a cp length.c to length.ttpasm, and then we'll take a look at the assembly version and ask, okay, how do we do this? So change all the beginning of a line to comment, the space, and then we can start from there. So typical entry code, okay, we initialize the stack pointer, make sure it is 0. And yes, this is the first time I use subtract D from D to 0 to put a 0 into register D. I just want to give you guys alternative way of doing the same thing so you can see it and recognize, oh, okay, we're just initializing the stack pointer. And hmm, yeah, yeah, but this says 1 byte, which is insignificant when you guys all have like 32 gigs of RAM on your gaming computer. But remember, TTP only has 256 bytes. So 1 byte is what, 0.4% already? Yep, that's kind of significant. So LDIA with .6 plus, and then we push it on the stack, and then we jump to main. When it returns, it's time to halt. And this is main. Main has one local variable called result. So main has exactly 1 byte for LVS, which is local variable size. It is the offset to the last local variable plus the size of the last local variable. That's all we need. And then we do the usual stuff for returning, LDBD. I'd like to use register B or C, just in case the function has anything to return, then I'm not going to interfere with that. Increment D, JMPB in this case. So now we need to allocate for the local variable and deallocate the local variable. So now we have LDI. I choose B anyway. So B with main LVS. Subtract that much from the stack pointer to allocate. And then at the very end, we need to do the deallocation. So we'll go ahead and change the subtract to an add. So now we can actually continue with the rest of the code. So are we doing okay so far with the program at this point? Okay. And you can see that when I write code, it is not linear. Okay. I go to the beginning and I immediately put in the end that matches the beginning. It's just like when I write the C code, I open the brace, I immediately close the brace, and then go back to insert lines between the braces. Okay, it's just the way that I do coding, and I found that this is really helpful because I don't have to worry about, okay, So how many close braces do I need here? Okay, because in many programs, you end up with closing multiple braces, kind of at the same time. With this way, it's automatic. I don't have to worry about, whether I have enough or too many close braces. Are they at the right places? I don't have to worry about those. All right. So, yes, result. Yep, correct. Yep. Because otherwise, the return code will be using the local variable as the return address, and it would just go to some la la land. Well, to be in this case, exactly location 4. All right. So now we have another concept to talk about. What is a literal string? Okay. A literal string, okay, this is how a literal string looks like. Okay. So this is also how the compiler gets the job done. It would actually create a quote unquote variable of sorts that you cannot see. Okay. So I'm going to start with two underscore as the name of the variable. Okay. And technically speaking, you can create a label with just underscores. So you can have one underscore as a name, and then two underscores as a different name, and three underscores as yet another name. Not a good idea, but you can do it. Okay. So I'm just going to say this is literal string one, okay, assuming that there might be multiple literal strings later on. And then the way you do it is really just use the byte to enter the ASCII code of each character or each letter one by one. Okay, so at this point, I'm going to cheat a little bit and I'm going to man ASCII to look up the code of tech. Oh, okay. Why does it? Let's see if I can scroll, but okay, fine. So we just look up TAK. Okay, so T is uppercase right here. Okay, so it's 84. I'm gonna have to write it down on something. We'll put it on the whiteboard. I just want to double check that we are recording. So most of the time, it is the process of writing this code that is important, not so much the finished product. So we have 84. Okay, that's too faint. Rim. Okay, 84. And then lowercase a is 97, I think, in decimal. Yep. And then K is just down a little bit, 107. And then we have exclamation point, which is on this side, 33. And then a null character. So those are the numbers that I need for the bytes. Okay. So now we can go back. Okay, go back here, and then just say, okay, byte 84. And the next one is lowercase a 97. And then the next one is K 107. And then we have the exclamation point, which is 33. And then finally the null character, which is a 0. Okay. So there are actually 5 bytes. Okay. So the literal string TAK exclamation point consumes 5 bytes. Okay. So now we look at this and go like, okay, we need to call the function with exactly that label. So the way we do it is, well, I guess that's exactly what you think it should be. We load the label literal string one into register A, and then we just push it on the stack. Decrement D, stda. So the address of what we just constructed is now pushed on the stack. That is our argument. Is that okay? So a literal string is a pointer to some place where the characters are actually located that there's no name, at least not visible to you, but the compiler does exactly what I just did. Okay. Then we still have to kind of specify the return address, and that part is fairly easy and template based. So now we have pushed both the argument and also the return address on the stack. We can now do a JMPI to length as a function. When it returns, we have to increment d exactly once to get rid of the argument that is sitting on the stack. The argument is a pointer, so it is only 1 byte wide in TDP. Okay, we are not incrementing 5 times because it's not the string that is on the stack. It is the address of the string that is on the stack. Okay, so that part is really kind of important. And now we can store whatever is in register A, which is the return value of length, into the local variable. So now we have LDI B with main result, add BD, STBA, and that should finish the operation. So now we go to length. Okay, this is length, and we say this is the entry point, and it has an argument. So we'll specify LVS to be 0 because we don't have local variables. That's kind of the whole point of going for the recursive version. And then LV string str as a parameter is at 1 byte from LVS because LVS specifies that there are no local variable. So that means the stack pointer is pointing directly at the return address. And that's why the offset from the base of the frame to string as a parameter is 1 off. Okay, so that one has to do with the return address. This one here has to do with the return address. All right, so now we can get to the end, specify the usual end code, LD, BD, increment D, JMPB. Now we are ready to, I mean, you can allocate 0 bytes and then deallocate 0 bytes, but I'm going to skip that, okay? So now we can specify exactly this return statement. Well, structurally speaking, it really is a conditional statement. So we evaluate a condition, and then we go to either the then branch or the else branch. So the first thing we need to do is get to str the value of str, not what it points to. Once we get to str, then we can get to what it points to. So once again, I'm not going to comment the program, but I will annotate by voice so that you guys can kind of get the program and then annotate yourself, okay? Because I think that really is a good way to study, okay? Because as you think about the code, you can then go like, okay, so what are we doing with this instruction? How does it relate to the C code or concepts in C code? So the first thing is to get the offset, okay? So we'll load the offset into register, let's say register B. Then we get to the address of the parameter. Then we get to the parameter itself. So at this point, B is a pointer to a character, okay, which is not what I want to compare. I want to know what it is pointing to and then compare what it's pointing to 0, okay, to see if whether there's a null character. So I may need to get this back again. So I'm going to put it into a different register, say register A. So at this point, register A is what str points to. Register B is str itself. Are we good with that concept? Okay. Hmm? Register B is literally str or whatever the parameter is. I'll show you on the stack. Okay, so when we run this code, we'll see what is happening on the stack, and then we'll say, okay, so and then we can specifically look at these two lines. Okay, so we'll put some comments here. Okay, so to remind ourselves, we need to take a closer look at this. Okay, so we're gonna say to do. Okay, uh, you know, confirm that B is the value of str, and then to do confirm, because later on in the spreadsheet I can look for the to do's like a search. Confirm that is what str points to. There we go. All right, so now we can check whether A is null or not. We'll take the shortcut, okay, use and AA. JCI to the else case in this case. So I go to length else 0. So that means that whatever is following is the then case. So I would write the entire structure of the if then else first and then come back and flash out the content. So I will first comment and say this is the then case. Whatever the then is going to have to have a JMPI to the end of the conditional statement. The else label starts here, do whatever the else has to do, and then we have the end if over here. So this is the else case. So I construct the entire framework first because otherwise I would forget. Okay, I would the most common thing that I forget myself is the unconditional branch to branch around the else case to the end of the conditional statement. That's my favorite mistake. Okay, so by doing it this way, I don't forget. Okay, but it is also important to use labels to kind of comment and say, okay, which part is the then and which part is the else, okay? Because now it is really clear to me that this is where we need to do the recursive case, and this is the place where I need to specify a return value of 0. And I don't have to do a single thing. Because if I end up here, the question is, how did I end up here? I end up here because of the JZI to else 0. But why would that branch? Because the Z flag is a 1. Who sets the Z flag to a 1? It's the AND AA. How can AND AA set the Z flag to be a 1? A is a 0 to begin with. Oh, okay, that's exactly what I need to do for the else case. That means I don't have to do a single thing. Okay, so I did a little bit of optimization in my head ahead of time. So, but you don't have to do it this way. Okay, your code does not have to be optimal, just has to be correct. So there we go. And so the then case is the only one that is a little bit kind of complicated. It's not too bad, okay, because we have str still in register B. So I can now say increment register B, push it on the stack, decrement D, stdb. So now we have pushed str plus 1 on the stack. And then we just need to push the return address. Okay, we can put it into whatever register A dot 6 plus. Oh, LDI. I like syntax highlighting. And then we decrement the stack pointer, stda, push it on the stack, jmp to the function that we're calling. Just so happens to be what I'm in right now. It doesn't change a single thing. It doesn't change a single thing about the caller callee agreement, even though they are the same function. There we go. And what should I do with the result? Well, we should add 1 to it to become my actual return value. So that means increment A would add that 1, okay, this one over here, and I should be done. All right. So I just did something horrible because I did not practice what I preach. What I preach is write the code in small chunks, okay, test it, and then test it again, and then write some more, right? So if I make a mistake anywhere here, it'll be fun to debug this one. Because I did not follow my own advice. Okay, so we'll see what happens this time. Okay, I'm kind of excited to try to find out whether this is going to work or not. Hopefully, it does not. All right, there we go. Submit length.ttpasm. I could possibly be the only professor that you will encounter who is excited about things not working. Because I can teach more when things do not work. There we go. Okay, so hopefully it's not working, but we'll see. So how do we know whether it works or not, right? So the way we know whether it works or not is to go to the end of the entire trace. Okay, so we just keep going. Okay, it's relatively short, so I'm pretty sure it's working. Disappointing. Um, we get to the hold instruction. The stack pointer is balanced. And then the last thing that we store is a 4 to the local variable. Ah, okay. It worked. Yes, it worked, unfortunately, because most of the time you won't get it working the first time. So I want to help you understand how to debug a program. So now, just because the program works doesn't mean that you cannot learn from this program and see how to debug a program that has a bug, because you can always inject a bug into the program. Okay, let's just say that you forget to do the increment D after the return, see what happens. Okay, or you use the wrong register for the AND. Instead of AND AA, you did an AND BB. Okay, and see what happens. Okay, so you can still kind of mess up the code and see what happens. And it's even better in a way because you know what it looks like when it works. So you can then compare to what it looks like when it does not work in different ways. Okay, so I think that can also be a learning experience. Okay, once the program is working like the first time, you can still go ahead and kind of mess it up and see if it continues to work or how it's not working, I should say. Okay, so, but we are not done with the trace yet, okay, because I want to show you what the stack looks like in this case. So the stack at the deepest point of the recursion would look like the following. We need a new spreadsheet for today, so we'll go back to not this folder. Where's my other folder? Okay, fine. Oh, I just saw it and then I clicked the wrong one. There we go. So we'll go ahead and add a sheet for today so that we can take a look at the stack at the deepest point of the recursion, and then we can verify whether that really is the case, in the trace. 2025 1110. There we go. So start with location 255. This is one location below that, and that we need 5. So 10. We need to get to at least here, I think. There we go. And look at the hexadecimal version. Deck 2 hex of this. There we go. And you can usually double click it. It finds out where the end row is. All right. I think that we might need one more location, but I could be wrong. So let's see. Go for a few more. All right. So the first location is the return to the entry code. Okay, so we don't know exactly what it is, but we know what it does. Okay, the role that it serves. So this is the return address to the entry code. So that means this location is going to be local variable result of main. And then below that would be the first invocation. So the first invocation is going to push the string itself at the very beginning. So this is going to be the literal string. We'll give it a name. We know the name because it's underscore underscore lit str1. And this is exactly what the label is supposed to be here. And this is going to be the return address to main. And then we know that is a non-null character. Whatever is at this label is uppercase T. It's not a null character. So that means we're going to go for the recursion. The recursion should push str1 plus 1. I'm going to use infix notation in this context. Okay, so it's just exactly the next location, which is lowercase a, which is not null. It's going to call again, but this time the return address is not back to main, but back to length. Okay, so it's a different address. And then after that, it sees lowercase k, which is also not null, so it's going to call again. So now we push literal string 1 plus 2, which is the address, the starting point of the next recursive call. And then the return address is also back to length itself. And then it's going to call again. This is a plus 3. which is finally the exclamation point, return address to length, and this is the last recursion, lit string 1 plus 4, which is the null character. So in this particular function call, okay, let me finish the stack first, or the frame. So in the last frame, the function realized that the pointer is pointing to a null character, and then it decides to return the value of 0. So this is what the stack should look like at the deepest point of the recursion. Um, I think I just kind of I messed up a little bit, okay, because column C is supposed to be the value that is on the stack, and then this one is supposed to be the row that that location is serving. So technically speaking, I really should fix that first. So give me a second to fix because I just need to look up the variable name is str. So this is str, this is also str, but I need to move it over here. Okay, just do the same thing. This is also str. Control X, put it here. Control X, put it here. And then this is str, like so. Okay. We can also find out, what the um, return addresses are, so I can actually fill in exactly what this is supposed to be. That's coming from the assemble tab. So if you go to the assemble tab, you can look at the return address from main. So this time it is at location 08. Okay, most of the time it's 09 because it takes 2 bytes to initialize the stack pointer. Today I chose to use the simpler way that only uses 1 byte. So that's a 09, and we can just kind of say, okay, this location is supposed to be a 09. And this is still unknown, but we know it's 0 to begin with, and then later on it changes to a 04. Yep. Huh? It I said normal is 09 because it's a LDI D0 that takes up 2 bytes, but this time it's a 08 according to the assembler. Oh, okay. Yeah, I'm sorry. I'm a habitual liar who does not even know when I'm lying. Makes me a perfect spy. Makes me a perfect double agent. You can ask me any question. I will pass the lie detector test with flying colors while spewing out complete non-truths and not even knowing that I'm spewing complete non-truths. All right, the return address to main is over here. It is right next to the JMPI instruction in main. So the main JMPI is where? This is main's own return. So the JMPI is, oh, right here. So the next location is a 2E. I'm trying to fill in as much as I can. So this way, if something goes wrong, I can tell you, I can tell right away. This one is return to length itself. So we go to length this time, and then right after the JMPI to length, it is location 1A. So we backfill that 1A over here. And that's going to be the same for the other 4, like so. Lit string itself also, we know what it is. So we go to the assembler, and then we look up string length. It is 3.9, and then 3A, 3B, 3C, and 3D. So now we go back and backfill those two. So this is supposed to be 3.8, I think. Is it 3.8? 3.9. Okay, 3.9. So this is 3.9, 3A. Oh, oh, there you go. So this is 3A, 3B, 3C, and 3D. There we go. All right. So this is important, okay? As an exercise, this is really important because it helps you really visualize what is on the stack. This is one frame. Okay, this is the frame of main. It consists of the return address and the local variable. Okay, let's color code it. So in a way, this is my way of helping to kind of document the concepts. This is the first frame of length. Okay, this is the first time we call length, and this is the frame of that. So we'll change it to the next available color. Hmm? Because main calls it, and then main finishes what it needs to do, which is using the return value to update its own local variable of result. No, str calls itself multiple times, and it unwinds the stack. Okay, let me finish this, and then we'll take a look. Oh, okay, that's good. Different color. We look at this, display of the frame. We'll call it Skittles. Look at the colors. Yep. Look at that. Ooh, nice. All right. So this is what we're predicting to be, what happens at the deepest point of the recursion. The stack pointer should go all the way down to F4. Okay. So in the trace, we can do that. We can look for that moment relatively quickly, because what we can do is to look at column D, and then we ask, when does register D get a value of, I cannot remember, F4. Okay, so that's what we do. Control, yeah, well, finding sheet is going to be okay because it's a very specific pattern. It's D equals to F4. It does not find it. Oh, yes. Okay. Okay. I was getting a little bit excited that the program was not working, and then it go like, yeah, it's working fine. Okay. Okay. So we see the last location is getting, the content of 1A. Was that what we expected? Yep. The next one is supposed to be a 3D. So let's see whether that's also what we got. Yep. So now we can kind of go back up, on the stack and kind of keep tracking that. So I did not forget your question, which is already marked as to do. So let's go all the way back to the beginning and then just search for the word to do. That makes it kind of nice to and easy to find, right? This is our first to do, and we have a whole bunch. All right. So we want to confirm this is the value of red str, and that is the case. It's a 39. 39 is str. This is the first invocation. And then with this one, we want to confirm register A is what it points to. It is 54 in hexadecimal. So 54 in hexadecimal is 5 times 16 plus 4, which is 84. That's the ASCII code of uppercase T. So does that help? Okay. hmm Into the memory. Yes, correct. Yep. And you can see that in the assemble view too. So in the assemble view, the byte lines, all it does is to consume one location, and then that location will store whatever the expression is expressing. It is showing in hexadecimal because that's how the assembler works. I mean, the assemble view works. Yep. hmm Yep. All right. So do we have any questions about string length, you know, as it is? There's no in assembly code, it has no uh, there's no notion of type. So you have all the instructions, that you can use. You have subtract, you have add, you have compare, you have and so on. But it doesn't understand ASCII code at all. It cannot interpret ASCII code. There's no way. It simply look at a char like so in C++ programming, a char is no different than a bit signed integer. So the only thing that allow you to display something like in the ASCII code is the magic of cout. So cout can look at a char and say, okay, when I print this out, I'm not printing the integer value. I'm interpreting this as an ASCII code and print the actual letter or punctuation mark corresponding to that, ASCII code. So that's the magic. So if you guys are interested, um, there is a feature in Logisim that can potentially be used to display something. I do not have an instruction to do it yet, but we can consider kind of implementing a new opcode that could be interesting. But I can show you first, what I mean by that. Or printer. Yeah, yeah. So the device that would do this is called a TTY, so which is also called a teletype. Okay. So when you go to a teletype, let's look at the points here. ASCII value of next character to write. So if I make a new instruction and include an ASCII, I mean, include a TTY device to the TTP ASM to the TTP, I can potentially, let your program to print stuff on quote unquote a screen. Okay, I see what you mean. So in this case, if you use a TTY and you send an ASCII code over, it will just print it as an ASCII code. If you want to print an integer, let's say you want to print 84 as 84, you actually have to go through some horrendously complicated code to look at the binary representation, which is native to the processor, and then convert that into digits in whatever base you want to use. So it's actually much more complicated to print something as an integer as opposed to the ASCII code because you have to go through actual base conversion in that case. So does that answer the question? So if you print anything to the teletype, it will only print it as the ASCII code. So if you have a value in a byte and you want to print the value of the byte in base 10, it's actually horrendously complicated given the architecture that we have. Yep, question? That is actually complicated. Yep. Yeah, so when you use C++ and you have a cin and you try to read from cin into say an integer, a regular integer, int, okay? you type normally in base 10, let's say 25, okay, 2, 5, press the enter key. So the 2 and the 5 and the enter key that you press on the keyboard, they are really just ASCII code when the when the C when the library function gets it. Okay, so the library function now has to look at the first two, and then look at the five, and then look at the return in and actually use code to convert that into the value that 25 in base 10 is representing. Yep. So things that you are used to in C++, a lot of that is actually much more complicated than you the first time you see it. Hmm. Yep. But this would be an interesting thing to add to TCP is for display, and it also has a keyboard as a component. Hmm? Yeah, so the keyboard allow you to type something and it will convert, what you type into the ASCII code, and then quote unquote, the the processor has a way to know whether there is something to get or not, and if there is, then it will go, kind of read that byte off of the keyboard. The reason why I do not include the TTP or the keyboard in TTP is because I don't have enough bytes to specify a program to really make good use of either device, because it takes a lot more code to kind of, okay, somebody just type in 26 on the keyboard. Okay, now I need to get the binary representation of 26. That's actually not easy, at least when your processor has no hardware multiplication or division. That makes it actually really, really hard. Hmm? Hmm. Yep. All right. So does that address the question? Yep. Okay, very cool. I'm gonna close this, discard. All right. So we'll go ahead and implement a second program, but probably without as many explanations. Okay. So we'll do string copy this time. We go back to the command line. Okay. And then we ask, okay, what exactly is string copy? Man, string copy. There we go. So string copy is copying the source to the destination, and it will keep copying until it sees the null character. Okay. And if you read the man pages, make sure you read all the way when it says caveats. If the destination buffer is not large enough, the behavior is undefined. So it tells you that, do not use it basically because it's not secure. But, we're going to use it as an example today. So we'll go ahead and start with length and then convert that to string copy, cpy.c. And now we just kind of change this to cpy. And this is our second argument. The first argument is going to be my destination, like so. And I can still use a good portion of the same code here. Um, what it returns is destination itself. So basically, this is a way for you to stack function calls so that whatever string copy returns, which is the destination with the content that is already copied, can serve as an argument to another function that will do further processing. And once again, people who complain about this is the code that is difficult to read, they will not like this. Okay, but that's the whole reason why string copy returns a value. Because if you think about it, it doesn't make sense. Okay, because the side effect is what it is supposed to do. It's supposed to copy all the characters from the source to the destination, and nothing else. Why do we want it to return the destination when it is an argument that is passed to the function? The reason why that is the case is so that you can stack your things. So in this case, okay, we are still going to use a ternary expression here, except we all will combine this with a comma expression. There is such a thing, okay? So the comma expression basically says, evaluate everything that are comma separated, but the last expression is the value to actually, it becomes the value of the entire comma separated expression. Okay, so this is a way for you to specify sequential operation, but without leaving the context of an expression. Yep. Yep. And yet, this is just regular C. All right. And then the last one has no operation, so I guess a zero is fine. No, it's not fine. It's fine because this is already returning the destination itself, so we're good here. Okay, so you can see the minor changes that I made here is really minor. The recursive call to link is now your recursive call to CPY or copy, and I just need to tell it, oh, the next location, or the buffer, okay, the destination for the recursive call is just one byte past the current one. Okay, now there's one more thing I need to do, which is to copy whatever string has to whatever destination is pointing to right now. So I just have to specify, this. Whoop, oh, wait. There we go. So we're gonna have to specify that operation, and you are not misreading this. This is supposed to be a single equal. Assignment is an expression with the value of whatever goes to the destination on the left-hand side. So I am totally using most of the regular C. This is not even C++. This is just regular C. But most of these features you guys do not encounter in CISP 360. So once again, let me explain this code. Okay, we may not even have enough time to do this. So this is an expression itself. The value of this expression is whatever the right-hand side is. So it has a side effect of also updating whatever the left-hand side is, but whatever is the right-hand side of the assignment becomes the value of the entire assignment expression. So we are still checking whether we are at the end of the string or not. If we are not at the end of the string, which means I just copied one non-null character, I do the recursive call over here. The recursive call is simply saying, okay, let's start with the next character or the address of the next character as the source. And let's start with the character next to whatever just received a byte as the next location. Okay. And if that is not the case, if this is null, that means I just copy the null character. Then I can do whatever here. Okay, it doesn't really even matter because the entire thing here, this entire expression, is comma separated. So it only cares about the second item in the separated comma separated list, which is destination. That becomes the actual return value of the entire thing. All right. So are we reading the C code okay? I do realize that this is not a conventional way of expressing the logic of string copy, but it is also a good opportunity to show you the alternative way of expressing the same thing, except it is the whole thing becomes one single expression. Okay, so uh, I mean, it is one way to do it, right? So we'll say this is my buffer, and we'll give it like we'll give it plenty of bytes here. So now we just have to say result. We want to check the result too. So we want to put a char star here. Result is going to get CPY offer like that. Okay. So this program should compile in C. Okay. So we'll check it out first. Make sure it does compile in C, and then we'll try to convert it into assembly. Okay. Hmm. So that's way. So it should only overwrite the first five locations. Hmm. So CGCC dash G dash O ST. Oops, this is CPY. CPY.C. GDB CPY. Put a breakpoint on line 11 so we can check both the side effect and also what gets stored in the result. So we run first. Okay, now we're at a breakpoint. Print result. That should be the same as buffer. So we can print buffer too. Okay, same thing. And we should also print. Oh, I just did both. Okay, fine. So we can see the side effect of copying. We can also see the return value that gets stored in result, which is the beginning of the string. So yes, so this is not just tech, it's talking about things that do not exist. It is not tech, hallucinating because we were talking about AI earlier, right? So it does work. What do you mean by remove the buffer? It did not remove the zeros. It just did not print the extra zeros. So when I say print result, it treats it as a C string, which means it only prints up to the first null character, but excluding the null character. The null character does not get printed. Sort of. Sort of. Yeah. Because when we say print result, it is using the convention of this is a null terminated string, and it only prints the non-null characters up to the first null. But when we print buffer, it knows the length of buffer, so it prints every single element of buffer in the second case. Yeah, because it knows buffer has exactly 10 bytes because of the way it is coded here. So when we say print buffer, the debugger actually knows all the information about buffer that it has a length of 10. So when you say print buffer, it just prints everything. Okay. Yeah. So I really doubt that we have enough time today to actually finish the program, but you can see that it's not going to be much more different compared to the previous one. It is going to be a little bit longer. Okay, but we can do it next time. All right. So today we do have a lab, and I'll let you guys get started with a lab earlier so you can finish earlier too. So the lab is a little bit out of sync compared to the lecture. The lab is going to start with just basic structure, which we have already talked about. So we will go ahead and start with this one. And we do the edits. Okay, give you guys today to do it. Today is November 10th, and the end time is 1:20 p.m. Canvas doesn't understand the 24-hour format, which is really annoying. Hmm? Uses AM PM. Yeah. All right. And I'm going to turn that on. Filter IP address and publish. There we go. All right. So you guys should be able to get into the lab now. Hmm? Access code is just struct. Yep. Hmm. STRUCT. All right. So I'm going to stop the recorder and start to